Hello, everyone. I hope you're all safe and sound. Welcome to the 20th lecture on analog and digital electronic circuits, in which we will study the BJT-based class ADE output stage. So we will analyze the class ADE output stage in the quiescent state. We will derive its voltage transfer characteristics. We will study its small signal output resistance. And we will look at some of the methods which are used to bias the class AD output stage. So a class AB output stage, as shown in this diagram here, is a variation of class B output stage, which is biased at a small non-zero current through this DC voltage VBB between the base terminals of the two complementary devices, which in turn, as I will show, ensures the conduction of Qn and Qp in the dead band of the BTC in order to avoid the crossover distortion. So instead of an abrupt changeover, the amplifier slowly and gradually transitions from the push towards the pull behavior and vice versa. From this circuit, we can see that the load voltage VL can be expressed in terms of the input voltage VI through either this loop or this loop. So if we go through this loop, then VL is given by VI plus VBB by 2 minus VBE of Qn. And if we go through this loop, then VL is given by VI minus VBB by 2 and plus VEB of QP, which can be written like this by taking the negative sign out common. So the voltage between this node and this node, that is between the base of Q1 and QP, is always equal to VBB. And since the voltage between this node and this node is the sum of the voltage VBE plus VEB, we see that the base emitter voltage of Qn plus the emitter base voltage of QP, they will always add to this constant VBB. So assuming that the two complementary devices are matched, this is actually a very important condition, that the two devices should be as closely matched as possible. Then under the quiescent conditions, that is when there is no signal applied at the input, we see that the load voltage is given by this expression and this expression, which can be obtained from equation 1 on the previous slide by simply putting Vi equal to 0. So from these two equations, we see that VBE of N and VEB of P, they add to VBB. So this will always hold. It's not just an expression for the operation under quiescent conditions, it will always hold. Furthermore, as a consequence of this constraint of matched devices, we observe that under quiescent conditions, the load voltage is 0, which means that when there is no signal applied, the output load voltage is 0, which in turn means that the DC content of the load voltage is 0. So when VL is 0 under quiescent conditions, from this expression, we can see that VBE of N is equal to VBB by 2, and VEB of P is also equal to VBB by 2. Under this condition, VBE is equal to VBN because the emitter is connected to the emitter terminal is connected to the load, so VE is equal to VL, which is 0. So VBE of N is equal to VBN. And since the emitter terminal of QP is also connected to the load, so VE is again 0. So VEB of P is equal to minus VBP because VE is 0. And VEB of P is VE minus VB of P. So we see that under quiescent conditions, when the load voltage is 0, the base voltage, which is equal to the base to emitter voltage for the Qn device, is equal to VBB by 2, and the negative of the base voltage, which is equal to the emitter base voltage of QP, is also equal to VBB by 2. So since the base emitter voltage of Qn and emitter base voltage of QP, they are the same, and the two devices are matched, they will contain equal currents. So the emitter current of Qn will be equal to the emitter current of QP. So under the quiescent condition, we call this constant current as the quiescent current and denoted by IQ. And it is given by Is times the exponential dependence on VBB by 2, because both of these, the base emitter and emitter base voltages, are equal to VBB by 2. So this quiescent current is clearly controlled by the base to base voltage VBB, and Is is the scale current for the matched devices Q1 and QP. So by properly adjusting VBB, we can set desired quiescent current in the class AD output stage. So unless class B output stage, which does not conduct in the quiescent state and hence does not dissipate any power in the quiescent state, class AB output stage dissipates this much amount of power per unit transistor in the quiescent state, because in the quiescent state Qn, the collector current of Qn, if we assume that alpha is almost 1, then the emitter current and the collector currents of Qn, they are the same. So the collector current of Qn will be IQ. Similarly, the collector current of QP will be IQ. So the power drawn from VCC will be VCC times IQ by Qn. And the power drawn from minus VCC will be equal to minus VCC times minus IQ, because IQ is pushed into the source, minus IQ is drawn by QP. So minus IQ times minus VCC again gives us VCC times IQ. So total power dissipation of 2 times VCC times IQ, and Qn dissipates VCC times IQ, and QP dissipates VCC times IQ. So in the quiescent state, class AB output stage dissipates VCC times IQ units of power per transistor when there is no signal applied at the input. When a positive voltage is applied at the base, so right at the instant at which the positive voltage is applied, and before before there is a change in the conduction of the transistors, VL is still 0. So this means that since Vi is applied at the base of the two transistors, VL is 0. This would mean that the voltage at the base of Qn, it will increase above VBB by 2 to this value, Vi plus VBB by 2, as you can see from this circuit here. So VBN is VBB by 2 and VBP is minus VBB by 2 under quiescent conditions. So as soon as we apply Vi, then the voltage at this node, it increases from VBB by 2 to VBB by 2 plus Vi. And the voltage here at this node, it increases from minus VBB by 2 to minus VBB by 2 plus Vi. So right at the instant at which this happens, before the change in conduction of the two transistors, this voltage is still 0. So this new base voltage appears across the base emitter junction of Qn, and this new base voltage here disappears across the base emitter junction of QP, because this is still 0, or you can consider it at ground before the change in conduction of Q1 and QP. So VBN increases to this value, VBP increases to this value, and like I said, VBN becomes equal to VBE, and VBP becomes equal to VBE of P. So increase in base voltages while the emitter is at ground means that the base emitter voltage of Q1 will increase, and the base emitter voltage of QP will increase. So increase in base emitter voltage of QP uh, will reduce the forward bias across the emitter base junction of QP. And the increase in base emitter junction of QN will increase the forward bias across the base emitter junction of QN. So this application of VI, positive VI, will cause QN to conduct more strongly than QP. And this will in turn increase the emitter current for QN. So the deficit between the emitter current of QN and the emitter current of QP will flow through RL, and we will designate that deficit by IL. So this is the load current flowing through RL. So as QN conducts more strongly than QP, IEN will increase, and since IEN is equal to IP plus IL, so IEN is equal to IEP plus IL. So previously these two currents, they were equal, so IL was 0. But now IEN is greater than IEP. So the deficit, the extra amount of current will flow through IL. That is, IL will be IEN times IEP. So the deficit in IEP will flow through RL as IL. So increase in the emitter current of QN will in turn increase the base emitter voltage of QN. That is, VBE of N will increase above its quiescent value of VBB by 2. So since from this equation, the base emitter voltage of QN plus the emitter base voltage of QP is always a constant equal to VBB, an increase in VBE of N will decrease VEB of P. So increased conduction in QN will cause the emitter base voltage of QP to decrease, which will gradually decrease the current and the emitter current IEP through QP. So this decrease in emitter current can be quantified by, again, looking at this equation. So like I said, this will always hold. So as VBE of N increases, VEB of P will decrease, which will decrease IEP. So we can quantify this decrease by using the expression for the collective current in terms of the base emitter voltage by assuming that alpha is almost 1 and ignoring the early effect. So this gives us VBE subscript N like this. So IEN is IS times exponential VBEN over VT. So we invert that relationship and we get this expression. Similarly, we can invert the relationship for QP and get this expression. And from the equation derived earlier, from this expression here in 4, we can write VBB as log of IQ over IS times 2VT. So log of IQ over IS times 2VT. And then we can take 2 as a power of IQ over IS, cancel VT, cancel log, and then cancel the IS square on both sides. We'll be left with this expression. So since IQ is a constant, increase in IEN for positive values of VI will cause decrease in IEP. So this expression together with this expression can be used to obtain the emitter current for QN in terms of the load current and the quiescent current as a solution of this quadratic system. So this quadratic system gives us IEN as a solution of this equation in terms of IL and IQ. So to conclude, we observe that for positive input voltage, transistor Qn, which is operating in the common collector configuration, pushes current IL through the load RL, which increases the load voltage VL in the positive direction. And this increase in the conduction of Qn, according to this equation, reduces IEP. So the conduction through QP is reduced. At large values of VL, uh, which corresponds to large values of IL and in turn large values of IEN, the current IEP conducted by QP becomes negligibly small. For negative values of VI, an exact opposite behavior is observed. So the voltage at the base of QP and QN, for negative values of VI, it decreases so the voltage at the base of QP is minus VDB by 2 under quiescent state, and the voltage at the base of QN is VDB by 2. So when we apply negative voltage VI, it decreases from minus VDB by 2 and VDB by 2 respectively to the values that I gave in this expression here. So VI, because it's negative, so the voltage at the base will decrease now. So this decrease in the voltage at the base will reduce the base emitter voltages of both devices. So a decrease in base emitter voltage of Qn will reduce the forward bias across the base emitter junction, whereas a decrease in base emitter voltage of Qp will enhance the forward bias across the emitter base junction. So QP will be caused to conduct more strongly than Qn, and the deficit in IEN will flow as minus IL through the load RL. So IEP, IEN is equal to IEP plus IL, which in turn gives IEP as IEN minus IL. So since IEP increases beyond IEN, IEN will be given by IEP plus IL, which means that minus IL will flow through RL. So minus IL will be a positive quantity. It will flow up the load resistor RL. And when that current minus IL is added to the smaller current IEN, we get a larger current IEP. So this difference in conduction flows as minus IL through the load RL in the upward direction through the load RL. So increase in IEP causes corresponding increase in the emitter base voltage of QP. And since the emitter base voltage of QP and the base emitter voltage of Qn, they add to a constant VDB. This increase in VEB of QP will cause a corresponding decrease in VBE of Qn, and this will further decrease the emitter current of Qn. So if I combine this equation 9 with this equation here 7, which always holds because this expression always holds, then I can express IEP in terms of the load current and IQ as a solution. I can express as in terms of IL and IQ as this quadratic system, the solution of which will eventually give us the emitter current flowing through QP. So again, to conclude, we observe that for negative input voltage transistor QP, which is also operating in common collector configuration, it pulls current IL from RL. That is, it causes minus IL to flow from RL. It causes IL to flow up the load resistor RL, which in turn increases VL in the negative direction. And this, because minus IL is increasing, and minus IL plus IEN is equal to IEP. From this relation, we see that since IEP is increasing, IEN will decrease. So increase in the load voltage in the negative direction will decrease IEN. And at large values of VL, the current IEN conducted by QN becomes negligibly small. So for small values of VI, so let's assume that VI is positive and very small. So at the moment it becomes positive, and before the change in conduction of QN or QP, VL is still 0. So the base voltage, which is strictly speaking equal to VI plus VBB by 2, is equal to the base emitter voltage of QN. So since VI is really small, so we can assume that that VB, the base voltage, the voltage at the base of QN, which is equal to the base emitter voltage of QN, is equal to VBB by 2. So for small positive VI, the base emitter voltage of QN, which will be momentarily equal to VBN, will cause the transistor QN to conduct. Similarly, for small negative values, so as soon as VI becomes negative, but is small, so at that moment, before any change in the conduction of QN and QP, the load voltage is still 0. So the base voltage, the voltage at the base of QP is equal to the base emitter voltage of QP. And strictly speaking, this voltage is equal to VI minus VBB by 2. So this, so since VI is really small, so we can assume it to be equal to minus VBB by 2. So base emitter voltage of QP is minus VBB by 2, which means that the emitter base voltage of QP will be VBB by 2. So emitter base junction of QP will be forward biased as well. So for small positive and negative values of the input signal, both transistors QN and QP will have forward biased emitter base junctions, and both transistors, they will conduct for small positive and negative values of the input voltage. This is why the two transistors in the class AB stage, they have a conduction angle of greater than 180 degrees. So this diagram shows the voltage transfer characteristics of the class AB amplifier. So since class AB amplifier operates much like the class B amplifier, we have maximum positive and negative swings of the load voltage remains unchanged. So maximum load voltage in the positive direction is observed when QN goes into saturation, and maximum load voltage in the negative direction is observed when QP goes into saturation. And for large signals, this curve between VL and VI has a slope of unity, which can be verified from equation 1 that I showed earlier. So the main difference between the operation of class AB and class B amplifiers is observed around VI equal to 0. So there we had a band. For class B amplifier, we had a dead band about VI is equal to 0. But here, because of the voltage VBB, both transistors Q1 and QP, they are biased and they are conducting even if there is no VI. So even when VI is 0, they conduct a quiescent current equal to IQ. So at VI is equal to 0, the load voltage is 0 because the emitter current for Q1 is the same as the emitter current of QP. That is, the same quiescent current flows through both transistors, and there is no load current. But around this at this point of VI equal to 0, for small positive and small negative values of VI, as I just explained, both transistors have base emitter voltages, such base emitter voltages that they both conduct at the same time. So this virtually eliminates the dead band and the resulting crossover distortion in the output load voltage. Remember that if you recall, the dead band was a result of period or the time when both QP and QN they were in cutoff. So since around this region both transistors conduct, there is no deadband, and when there is no deadband, there is no crossover distortion observed in the output voltage across the load. We can reach the same conclusion of elimination of crossover distortion by analyzing the output resistance of class ADE amplifier. So it is the resistance seen between this output node and ground. So here in this figure on the left, I have drawn the AC equivalent circuit of class ADE amplifier, in which I have short circuited the DC sources to ground. And I have also, for the computation of output resistance, I have also short circuited the input signal VI to ground. And RI denotes here the internal resistance of the source VI. So looking at the circuit, we see that also please note that I have replaced the transistor QN and the transistor QP with the small signal T models. So this is the small signal T model for QN, and this is a small signal T model for QP. So I wish to find the resistance between this node and ground, looking into this node. So I can simplify this computation by observing that R0 of N and R0 of P, they are in parallel, and they appear between this node and ground. So I can remove these resistances, and I can find the resistance at this node, between this node and ground. So that I do by analyzing the circuit given on the right here. So in order to find the resistance between this node and ground, looking into this node, I connect a voltage source between this node and ground, which pushes the current Ix into this node. So the ratio of Vx to Ix will give me the resistance between this node and ground looking into this node, which in parallel with R0N, in parallel with R0P, will give me the output resistance of the amplifier, which is denoted by R out. So looking at the circuit, I designate the voltage at this node with respect to this node, that is the voltage across Ri of this node with respect to ground, as VRI. And I can express VRI as Vx plus VBEN, or Vx, which is the voltage at this node, minus VEBP, which will give me the voltage at this node, which is the same as this node. So VRI, which is the voltage across Ri, is equal to VBEN plus Vx, or is given by Vx minus VEBP. So from these two expressions, I can see that VBEN is equal to minus VEBP. So these are small signal quantities. Furthermore, I can write the current Ix in terms of the currents through REP and REN. So Ix is equal to, so the current through REN, if I write VBEN over REN, then that is the current through REN in the downward direction. And VEBP over REP is the current through REP in the downward direction. So this current plus this current Ix is equal to this current. So I can invert this relation, and Ix will be VEBP over REP minus VBEN over REN. So this is the downward current through RN, this is the downward current through REP. So this is the downward current through REN, and this is the downward current through REP. And using this expression, I can replace VEBP with minus VBEN, and I can take minus VBEN common, and I'll be left with 1 over REP plus 1 over REN, which is the inverse of the parallel combination of REN and REP. Furthermore, I can write VRI in a slightly different form. So I can write VRI by finding the current through RI flowing in this direction, and then multiplying by Ri. So the current flowing through Ri is the sum of the currents flowing in this branch and in this branch. This current is given by GMN VBEN minus VBEN over REN. And this current is given by VEBP over REP minus GMP times VEBP. So I write VRI like this, GMN VBEN minus VBEN over REN plus VEBP over REP minus GMP over VEBP. So this is the current flowing through RL into the RL through the lower branch, and this is the current flowing towards, this is the current flowing towards RI through the lower branch, and this is the current flowing towards RI through this upper branch. So this is the lower branch and this is the upper branch. So I add the two currents and I multiply by Ri, multiply the sum by Ri, I'll get the voltage of this node with respect to this node, which is VRI. So I can replace this minus VBEN over REN plus VEDP over REP with IX. So this times Ri is IXRI, and I can use this expression again and write this as plus GMP VBEN, and then take VBEN common, and I'll be left with Ri GMN plus GMP times VBEN. Furthermore, I can replace VRI with VBEN over VBEN plus Vx. So now I can use this expression to write VBEN as Ix times the parallel combination minus Ix times the parallel combination. And then I can collect the Ix terms on one side, Vx on the other, and find the ratio Vx over Ix, which will be, after some simplification, equal to this expression. So this is the resistance between this node and ground looking into this node. So if I assume that this input source is ideal, that is Ri is 0, then this ratio Vx over Ix will simply become the parallel combination of REN and REP. So under this assumption of ideal voltage source, Vx over Ix is equal to this factor, and the output resistance is Vx over Ix in parallel with this factor. So this gives me the expression for R out under this assumption. And since R naught is much greater than Re, so this parallel combination is much greater than this parallel combination, which means that R out is approximated by the parallel combination of REN and REP. REN is VT over IEN and REP is VT over IEP. So you can open up this parallel combination and simplify it to get this expression. So what this expression shows is that in the region around Vi equal to 0, so around the origin of the VTC, as IEN increases, IEP will decrease because the conduction will gradually shift from Qn towards Qp. Similarly, when Vi decreases in the negative direction in its vicinity, IEP will increase and IEN will decrease because the conduction will gradually shift from Qn towards Qp. So around Vi equal to 0, around the origin of the VTC, as IEN, for example, as IEN increases, then IEP will decrease. So this will keep the denominator almost constant. On the other hand, if IEP about the origin or small Vi, if IEP increases because of the swing of Vi in the negative direction for small values, if IEP increases, then IEN will decrease, which will again keep this denominator almost constant. So this R out remains almost constant for small values of Vi about the origin of the voltage transfer characteristics of the amplifier, and which is the reason why there is no crossover distortion in the output, because a constant output resistance will keep the voltage gain of the amplifier constant. And since the slope of the voltage transfer characteristic is equal to the gain of the amplifier, voltage gain of the amplifier, the slope of the VTC remains constant about the origin, which essentially eliminates the dead band in the VTC, because in that dead band, where we do not have any output, the slope is 0. So if the slope does not change, there is no dead band in the VTC, and hence the crossover distortion in the output is eliminated. However, please note that for large values of the input voltage, either IEN or IEP will be large, which will eventually reduce the output resistance. So R out will be small, comparatively smaller at relatively large values of the input voltage. There are different methods of generating this base-to-base biasing voltage for setting up the quiescent current in the class ADE amplifier. One of them is the biasing using diodes. So instead of we implement the voltage VDD between the base terminals of Q1 and QP through the forward bias diodes D1 and D2, and in order to generate enough voltage between the base terminals of Q1 and QP to keep them conducting in the quiescent state, these diodes D1 and D2, they need to be forward biased, because this VBB voltage must equal about 1 volt or so that it is divided equally between the base emitter and emitter base junction of Q1 and QP respectively in the quiescent state to keep them conducting. And we know that when diodes are forward biased, their forward bias voltage is about 0.5 to 0.7 volts. So these forward bias diodes, they will serve the purpose of generating enough voltage between the base terminals of Q1 and QP to keep them conducting in the quiescent state. So I bias here, the ideal current source labeled I bias is used to keep, one of the purposes is to keep these two diodes in the forward bias mode. So assuming that the diodes are matched devices under quiescent conditions, that is when no input signal is applied, because the same current flows through the diodes and the diodes are matched, their forward bias voltages will be equal. So VD1 will be equal to VD2, and since VD1 plus VD2 is VBB, so VD1 and VD2, they will be equal to VBB by 2 each of both of these, VD1 and VD2, they will be equal to half of VBB. So the diode current under quiescent conditions, which will be a constant, that is why I have denoted it with capital I, capital D. This will be given by the usual exponential dependence on the forward bias voltage. Since the forward bias voltage is VBB by 2, so it will be given by IST times exponential of VBB by 2 over VP, where IST is the scale current for the diodes. And we know from equation 4, where we define the quiescent current, that exponential of VBB by 2 VP is equal to IQ over IS. So IQ was defined as IS times exponential VBB over 2 VP, where IS is the scale current of the output devices. So we can replace this exponential factor with IQ over IS. So we can write the diode current as in terms of the quiescent current through the ratio of the scale currents of the diode to the output devices. So from this equation in 16, you can see that the quiescent current can be set by the relative size of the diode with respect to the output devices, because the scale current depends on the emitter base junction area of the device. So the quiescent current is set by this relative size of the diode with respect to the output devices and the diode current. So if we denote the current gain of the output devices by beta, we can see that this source I bias, it provides the base drive of Qn, that is, it provides the base current for Qn, denoted by IBN, and the forward bias, the diode current, which is required to keep the two diodes in forward bias mode, that is ID. So under quiescent conditions, both Q1 and QP, they contain collector current of the IQ. So Q1 will contain IQ, QP will contain IQ, and the base drive of Qn is then its collector current divided by beta. So Under quiescent conditions, IBN is IQ divided by beta, and ID is given in this equation to be IQ times IST over IS. So if we define the ratio of the scale current of the output devices to the scale current of the diode as N, where we have assumed that the diodes are not only matched with each other, but they are also matched with the output devices, except in the area of their emitter-base junction. So the diodes can have different area of the emitter-base junction than the area of the emitter-base junction of the output devices. So this ratio is then, since scale current is proportional to the area of the emitter-base junction, so this ratio is then given by the area of the emitter-base junction for output devices to the area of emitter-base junction for diodes. So N is the relative size of the output devices with respect to diodes, and putting this back in here, so we can replace ISP over IS with 1 over N, and we can take IQ out common, so we'll be left with 1 over beta plus 1 over N. And later on, in fact, in a minute, I'll show that N cannot be made arbitrarily large. So usually and typically beta is much greater than N. So 1 over beta will be much smaller than N. So 1 over beta plus 1 over N will be approximately, or can be approximated as 1 over N. So we'll get IQ over N as an approximation to the biasing current I bias, which gives us the quiescent current in terms of I bias through N. So IQ will be, from this equation, is equal to N times I bias, where this is how we have defined N. The biasing current should be designed so that it provides the maximum base drive for Qn, and also the minimum current required to keep the two diodes forward biased. That is, I bias divides into the base current of Qn and into the diode current. So when we apply a signal, the output load voltage will swing in the positive and negative direction. When it is swinging in the positive direction, the current is pushed into the load through Qn. So Qn is conducting. So as the load voltage increases, load current increases, which means that the emitter current of Qn is increasing, which in turn means that the collector current of Qn is increasing. So at the maximum peak at the peak value of the load voltage, the current conducted by the transistor Qn will be maximum, and hence the base current of Qn will be maximum. So that is the maximum base drive. So I bias should be designed such that so the base drive will vary when there is no signal. The base current of Qn will be small, and when we apply a signal and at the peak value of the output voltage, the base current of Qn will be maximum. So base drive, which is the base current of the transistor Qn, base drive of Qn will vary. So I bias should be enough to provide the maximum base drive while keeping the diodes V1 and V2 forward biased. So this means that I bias should be equal to the maximum base drive of Qn plus the diode current required to keep the diodes forward biased, which in turn means that I bias should be greater than IL peak over beta, because IL peak will be the maximum emitter current, which is approximately equal to the maximum collector current. So maximum collector current divided by beta will give us the maximum base drive. So IL peak over beta is the maximum base drive. So you should one should design I bias such that it is greater than this quantity. The surplus will flow through the diodes, keeping them forward biased. So like I said, ID is the diode current, which is required to keep the diodes forward biased, so that in such a way that the variations in the diode voltage due to variations in the diode current, because the base drive will vary, and I bias is provided by, at least in this circuit, it is provided by a constant current source, so I bias is constant. So when base drive will vary, this current will vary. So ID should be the quiescent current ID should be such that when there are variations in the current through the diode due to the variations in the base drive of Qn, the corresponding changes in the diode voltage, they should be very small. And IL peak is the peak value, like I said, is the peak value of the load current provided by Qn. So one should keep in mind that as Qn pushes current through the load, like I said, base drive for Qn will increase, which will decrease the biasing current for the diodes. So there will be variations, like I mentioned, in the current passing through the diodes. And strictly speaking, this will change the forward bias voltage of the diodes, and hence it will change. It will cause changes in VBB. So VBB may not be constant if these changes in the diode voltage due to the change in diode current induced by the change in the base drive of Qn, if this change in VBB is significant. So if this change in the base-to-base voltage is significant, then the VBB will not be constant anymore, and hence we need to analyze the class ADE amplifier in this situation again to reflect this change in the base-to-base voltage of Q1 and Qp. So from this equation in 19, we can see that since N, which is the ratio of IQ, so N was defined by the relative size of the output devices with respect to the diodes, so it is IS over ISP. Furthermore, from this equation, N is the ratio of IQ to I bias. So this constraint in 19 puts a constraint on the value of N. So N being equal to IQ or I bias, and I bias being greater than this value puts a constraint on N, which is given by this. So N should be smaller than IQ over this maximum base drive. Because I bias should be greater than this maximum base drive, IQ over this N should be smaller than the ratio of IQ to the maximum base drive, which can be this in turn this ratio can be written like this. So N should be smaller than this number. So this means that we cannot make N arbitrarily large. In other words, N is made large if the diodes are made smaller compared to the output devices. So this in turn puts a constraint on the size of the diodes, that we cannot arbitrarily decrease the size of the diodes relative to the size of the output devices. Here by size I mean the emitter-based junction area, because emitter-based junction area will directly define the size of the device. So since typically the quiescent current is small compared to the peak load current, that is, it is typically less than about 10% of the peak load current. So this constraint on N, because IQ is typically small, so this is a so IQ over ILPQ is since IQ is less than 10% of this, so this ratio of IQ over ILPQ, this will be about 0.1 or less. So this factor will be less than equal to about 0.1 beta. So this means that N cannot be made arbitrarily large, which means that the diodes, they cannot be made arbitrarily smaller compared to the size of the output devices. So this is a disadvantage of this pricing scheme, that it puts a constraint on the maximum base price. The relation between the biasing current and maximum base drive puts a constraint on the relative sizes of the size of the diode relative to the size of the output devices. However, we observe one very important advantage of this scheme, which is the protection against thermal runaway. So thermal runaway is a phenomena, as the name suggests, in which if not checked, then it can damage the class ADE amplifier. So what happens is when during conduction, when the temperature of the devices it increases, then we know that for constant, because the collector current of a device depends on the scale current as well as the thermal voltage, and the scale current is a very strong function of temperature. So at fixed VBE, if the temperature of the device increases, then its collector current will increase. So when the collector current increases, the power dissipation in the device, it increases, which in turn increases the temperature again. So this increase in temperature will increase IEC again, which will increase the power dissipation and the temperature again. So this is a forward feedback mechanism, which just keeps on increasing the temperature of the device. And if not checked, then obviously it will raise the temperature of the device to a point where the device will get damaged. So hence the name thermal runaway, that the situation runs away thermally, gets out of control if not checked. So biasing using diodes provides an inherent protection against this phenomena of positive feedback mechanism. And we can observe this from this circuit here, that if the diodes are in close thermal vicinity of the output devices, then an increase in temperature of the output devices will also increase the temperature of the diodes. So if we assume that the current through the diodes is not changing appreciably, is almost constant, then increase in temperature of the diodes will reduce their forward bias voltage. So when the forward bias voltage, so when the temperature of the output devices is increasing, collector current is increasing, the temperature of the diodes also increases if the diodes are in thermal vicinity of the output devices, which will reduce their forward bias voltage. So when the forward bias voltage of the diodes is reduced, VBB will decrease. So the decrease in the base to base voltage will reduce the base emitter and emitter base voltages of the output devices, which will reduce the collector current conducted by the output devices. So this provides a negative feedback mechanism, and it tries to counter the increase in the collector current due to increase in temperature, provided that these two diodes, which by the way can be realized or implemented as diode connected transistors as well. So provided these two diodes, they are in close thermal vicinity of these transistors. So in order to achieve this, typically these diodes are mounted on these output transistors, so that the increase in temperature of the transistors, it increases the temperature of the diodes proportionally as well. Another method for the provision of this voltage VBB between the terminals of Q1 and base terminals of Q1 and QP is shown in this diagram here, in which this current I bias, it feeds this two-terminal network made up of the resistors R1, R2, and the transistor Q1. So it is called biasing using VBE multiplier. And why is it called VBE multiplier? Because if we analyze this this circuit, and if I represent the current flowing through this resistor R2 as IR under quiescent conditions, then ignoring the base drive for Q1, that is ignoring the base current of Q1, IR units of current will flow through R1. So IR will flow through R2 and through R1. So R1 and R2 will be essentially in series. So IR times R1 plus R2 will give us the voltage of this node with respect to this node, which is VBB. So VBB is approximately IR times R1 plus R2, where IR in turn, because it is the current flowing through R1 as well, under the assumption that there is no base current. So the voltage across R1 is the base to emitter voltage of Q1. So IR is approximated as VBE1, which is the base to emitter voltage of Q1 divided by R1. So we can replace IR with the VBE1 over R1 and multiply by 1 over R1 inside the parentheses to get this factor. So VBB is obtained by multiplying the base emitter voltage of Q1 through this factor of 1 plus R2 over R1. And this is the reason why it is called TDE multiplier, because the base to base voltage is set up by multiplying VBE of Q1 to this factor. So by adjusting this factor, we can yield a value of VBB, which in turn sets the desired quiescent current IQ in the class ADE output stage through the relation that we derived earlier, that is IQ is IS times exponential of VBB by 2VP. So adjusting this factor gives us a VBB that can set the desired quiescent current in the output stage. The value of VBE1 in turn can be obtained if we ignore the base drive for Qn. So this is an approximation that I will talk about in a minute. But if we ignore the base current of Qn, then the biasing current is divided into IR and the collector current of Q1, which means that the collector current of Q1 will be approximated by I bias minus IR. So VBE1, which is the base to emitter voltage of Q1, is related to the collector current of Q1 through this relation. So in this relation, we can approximate IC1 like this, under the assumption that IBN is 0. So knowing and IS1 here is the scale current of Q1. So knowing I bias and IR, we can find VBE1. So like I said, this approximation of ignoring the base current, it can work pretty well under quiescent conditions, because the base drive of Qn under quiescent conditions is small. Like I mentioned earlier, the quiescent current is about 10% of the peak load current. So quiescent current is small, and which in turn makes the base drive of Qn under quiescent conditions even smaller. Plus, when the load voltage is swinging in the negative direction, then the conduction is provided by QP. So QP is pulling the current, the load current from R. Q1 is not conducting for negative values of the load voltage. Although the changeover is gradual, so when the input voltage is 0, Qn is conducting a small quiescent current, and as the load voltage increases in the negative direction, the conduction gradually shifts from Qn to Qp. So during the negative swing of the voltage, the load voltage, we can safely say that the conduction through Qn is very weak, which means that the base current of Qn is very small. So under quiescent conditions and during the negative swing of the load voltage, we can safely ignore the base, or at least the approximation that the base current of Qn is zero is not that bad. However, the base drive of Qn can become large at and near the positive peak of VL, because when the output voltage, the load voltage is swinging in the positive direction, Qn is conducting more strongly, and at its peak, Qn is conducting the most current, which means that the base drive will be maximum at the positive peak of VL. So, so if we assume that the base drive is not negligible anymore, then we need to include this in this equation, which means that when we include the base drive of Qn, then IC1 will be I bias minus the base drive of Qn minus IR. So there'll be an additional factor of minus IB of N. So this will further reduce IC1. So this, so if you ignore IDN, then we'll have an overestimate of IC1. Whereas at the peak of VL, the collector current of Q1 will be smaller than this value. However, this difference in IC1 brought upon by this approximation is logarithmically mapped to VBE1. So which means that this difference in IC1 is not proportionately mapped to VBE1. It's logarithmically mapped, which means that it is even smaller. It reflects as an even smaller difference in VBE1. So the difference in the value of VBE1 obtained by this approximation is not that significant, because this is a logarithmic dependence of VBE on IC. So if you recall, then a logarithmic dependence goes like this. So in order to induce large change in VBE1, IC1 must change by very large amounts. So typically, this difference in IC1 by neglecting the base current is not that large. That is, when it is mapped logarithmically to VBE1, the resulting difference in VBE1 is not significant. So this is what I've written here. This decrease in current is mapped logarithmically into VBE1. So this logarithmic dependence results in negligibly small changes in VBE1, which means that there is corresponding change in VBB and IR. They will be negligibly small. So VBB and IR, they will be almost constant during the positive swing of the load voltage, because during the positive swing, the base current will increase, and this decrease in IC1, it will produce negligibly small change in VBE1, keeping VBB and IR almost constant during the positive swing of the load voltage, and as well as the negative swing of the load voltage, because during the negative swing, the base drive itself is pretty small. Furthermore, like the diode biasing scheme, we can see that this biasing scheme also provides protection against thermal runaway. So in exactly the same manner, that is, VBB will decrease to counter the increase in output collector current if transistor Q1 is in thermal vicinity of the output devices. So if the temperature of the output devices increases, so let's say if the temperature of Q1 increases, then at constant VBE, its collector current will increase. If this transistor Q1 is in close thermal vicinity of Q1, then for this, assuming that the collector current is constant, its VBE will decrease. So when the base to with the increase in temperature, so when the base to emitter voltage it decreases, VBB will decrease. So decrease in VDB will decrease the base emitter and emitter base voltages of Q1 and QT, which will counter the increase in IC in the first place. So, but then again, the condition is that Q1 must be in close thermal vicinity of Q1. So the change in temperature for Q1 is proportional to the change in temperature of the output devices. So that the decrease in VBE and the corresponding decrease in VBB is enough to counter the increase in IC in the first place. Finally, this is a variation on the biasing scheme using VBE multiplier, in which we have connected the base terminal of Q1 with a potentiometer. So the total resistance here in the upper branch is R2 plus some fraction of this potentiometer, and this resistance here in the lower branch is R1 plus some portion of the potentiometer. So by changing the value of this potentiometer, we can change this ratio of R2 over R1. So this gives us manual control on this ratio of R2 over R1. So by adjusting the potentiometer, we can adjust the ratio of R2 over R1, which will give us a VBB that can be used to set the required value of the quiescent current in the output stage. So the required value of the quiescent current can be set or can be monitored by changing this this multiplier 1 plus R2 over R1 through this arrangement. So by changing the value of the potentiometer, we can directly observe the change in the quiescent current. This in turn provides a method of manually setting the quiescent current in the output stage of the amplifier. So this brings us to the end of this lecture. Thank you very much for your time, and I will see you in the next class. Take care.